Alrighty, in this video we are going to look at volumes on a base, which are also called volumes of a solid with a known cross-section. We're going to take some of the same ideas that we looked at when we took a volume by revolving a two-dimensional region around an axis. We're going to take some of those same ideas and apply them to a different concept here. We are no longer in the world of revolutions. We are in the world of building something up off of a base. So this is a little bit tricky to visualize, so I'm going to do my best to try to explain this. If you can picture this axis that I've drawn, this is your x-axis, and your y-axis, let me make that a little better, my x-axis and my y-axis. What I'm trying to show here is that your normal coordinate plane, your Cartesian coordinate plane, your x-y axis, is lying flat on the page. And what I'm going to do is draw myself a circle that has a certain equation. So x squared plus y squared is equal to 4. This is a circle that has a radius of 2. Remember that the area or the equation of a circle is x squared plus y squared is equal to r squared. So if 4 is r squared, then r must be 2. So if I were to try to graph this circle, I'm going to go 2 units over and 2 units up and 2 units to the left. 2 units down, and this is a little bit weird, I'm trying to draw a circle that is lying flat on the ground. So you do your best to picture that. So I've taken this picture and I've put it flat. It's flat on the ground, and that's what I'm looking at here. And now what we're going to do is we're going to let triangles come up out of the page, come straight up out of the xy axis. So it's sort of like your z-axis, your three-dimensional coordinate plane here. We're going to have triangles growing up out of this circle, and the triangle size is going to be determined based on where you are at in the circle. So we're going to have equilateral triangles. So an equilateral triangle has all the same side lengths, and these things are growing up out of this base, the circular base. So I'm just going to look at one particular cross section. I'm going to look at the one that is lying right in the middle of the circle. I'm going to draw that for you. So there's what we've got. The length of the side is determined by the circle at that point, and the length there would be 4. If the radius is 2, I'm spanning the entire diameter, so this would be a 4-sided, or a triangle that has the lengths of side 4. And as you move out to the sides, those triangles get smaller, right? At this point, the triangle would be a little bit smaller. And then out here on the end, it would be really, really small. And the same thing is going to happen on the other side. So the shape that we're going to get when we do this is going to look kind of like this. This is your bird's eye view here looking down. You've sort of got this ridge line. And then if you look at it from the side, you can see your cross sections here, your triangle cross sections. And when you put all these triangles together, you're going to get this continuous sort of arc. And this is all coming out of the circular base. So this is the type of situation that we're talking about when we talk about volumes on a base or volumes of a solid with a known cross-section. When we say that we have a known cross-section, it means that I know that the cross-section is, in this case, an equilateral triangle. We could have the same exact situation, only the cross-sections would be, let's say, squares. So if that were the case, again, here I have the circular base, same equation as the last one, x squared plus y squared is equal to 4. And this time we're going to have squares growing up out of this thing. So a square, obviously, all the sides are the same. So I'm determining the side length based on where I'm at in the circle. So the center one would be the biggest square. As I move out to the sides, the squares would be a little bit smaller. And then way far out here, they're going to be real small. So if you were to try to picture what this thing looks like, you would end up with this sort of unit. It would have these ridge lines going back down around, and the squares would be sort of sitting like this. Little squares out here on the ends, big squares in the middle. So the question is, how do we find the area of such a wonky-looking cross, or wonky-looking structure? And the answer is, we're going to go back to this basic idea of adding up an infinite number of infinitely thin shapes or cross-sections. And remember here that A of x represents the area of a single cross-section. So let's go ahead and try to deal with that last example where we have a circular base and we have squares growing up out of the base. And let's try to figure out how we're going to deal with this. So what we know is that the area of a cross-section, A of x in this case, is going to equal the base times the height. It's going to be A squared. I'm just going off of this arbitrary A value that I am using to talk about the length of the side of the square. So the question really is, in the same way that when we did a volume of revolution, we had to ask ourselves, what is the radius, what is the big radius, what is the little radius, depending on if it's a disk or a washer. Here we have to ask ourselves, what is A? What is the length of the side of a square? And to answer that question, I go back to the picture of this circle, and I recognize that the distance from the top of the circle to the bottom of the circle, obviously that distance is always changing, but that is the distance that I'm looking for. So to shed some light on that, x squared plus y squared is equal to 4. Remember, that is the equation of our circle. I can't do much with this because right now this thing is implicitly defined. I want to explicitly define this in terms of, in this case, my y direction. This is remember, if this is my y-axis, I want to know some distance in the y direction. So I'm going to solve this equation for y by subtracting x squared and taking the square root, and there I'm left with, 4 minus x squared. And here we need to ask ourselves, what does this represent? What is y? And what this is the y direction. Whenever we measure a y direction, we're always measuring the distance from the x-axis up to the function. That vertical distance is y. So if I look just at the picture of the base, here's what I'm saying. The distance from the x-axis at any given point up to the function, that's y, right? If I'm over at this x value, that little distance is y. If I'm in the center, that distance is y. And we can check this. At the center, we know that the radius is 2. So we know that that distance should be 2 in the center when x is 0. So let's check that out. If we plug x equals 0 into this equation that we've just generated, if you plug 0 in for x, you're going to have the square root of 4 minus 0 squared, which is 4 minus 0, and the square root of 4 is 2. So we're good. We're verifying to ourselves that the y distance is the distance from the x-axis up to our output value. And this is important because that is not this a value that we're looking for. A is the distance from the top of the circle all the way down to the bottom of the circle. I don't want the distance from the x-axis up. I want the entire, let me make this in blue, I want this entire distance. That is the distance of the base of the square, which, of course, is the same distance as the vertical component coming out. So I want to know what are these distances. And this is easy. This is good news. Because if I know that this vertical distance, y is equal to the square root of 4 minus x squared, is the distance from the x-axis up, all I need to do is double that to get the whole length of the side of a square. So 2 times y, which in my case here would be 2 times the square root of 4 minus x squared. This is the length of the side of a square for any value of x within this circle. This is A. So knowing that, I can actually figure out what a of x is. I can substitute my 2 times the square root of 4 minus x squared back in for a, and that will give me my a of x. My a of x statement. So I'm going to write a squared, but instead of a, I'm going to write all this, 2 times the square root of 4 minus x squared. 2 times the square root of 4 minus x squared. And what am I doing with it? I am squaring it. So there it is. So I can simplify this before doing any calculus. 2 squared is 4, and then the square root of 4 minus x squared is 4 minus x squared, and this of course simplifies to 16 minus 4x squared. This is the area of a cross-section at any given point. If we go back to the picture that we drew of our circle that has a radius of 2, I should be able to verify that the square growing out of this thing along the center line should have an area of 16, because this is a side length of 4, meaning that this side length would also be 4, and 4 times 4 is 16. And that's true because at this moment x is 0. If you plug 0 in to this equation, you're going to have 16 minus 0, which is 16. So we're good. If I want to know what is the area of the cross-section at 1, I can plug 1 in for x and get 16 minus 4, which is 12. The area of that square is 12. Pretty cool. So what I want to do is add all these things up, an infinite number of infinitely thin squares that have this area along my x-axis from negative 2 to positive 2. So we're going to go from negative 2 to positive 2, 16 minus 4x squared dx. Don't be tempted to square this again. You've already squared it up here when you solved for a of x. And this now is fairly easy to antidifferentiate and solve.